Hello, everybody. Let us start our discussion today and let us start by reminding ourselves of what was Christopher's symbol. We are still discussing curvilinear coordinates. That's the coordinates where the basis vectors can change at different coordinate positions. It's called curvilinear coordinates because if you want to draw the one forms, they will look like curves instead of plain planes. So there will be curved surfaces. All right. So let's see where did we define Christopher's symbols. Remember, we were taking derivative of an unit vector as the coordinate changes, and even before I write down what we wrote this as, remember this is a vector which has d components. Beta is the level. It's a label tells you which unit vector it is, or should I say basis vector, which basis vector it is. So you are essentially taking derivative of 4 different functions here, if it's a 4-dimensional system. And what did you write this as? We said we will write this as some type of components of the basis vectors. And this is what we call the Christoffel symbols. So this was the defining factor of the Christoffel symbol. Now, you see, it is clear that both mu, b, and alpha can have d values. So this is the thing which has d cube components. So this has d cube components. So this was our definition of Christoffel symbol. This was defined as this. And then we explicitly wrote down the covariant derivatives for the vectors and one forms. Let me add to those the covariant derivatives of second rank tensors also. So let me list different covariant derivatives here. So start with one form. The notation is semicolon. This is the normal derivative. For the one form, I will get a minus sign, the Christoffel symbol. Now the derivative is taken with respect to x alpha in this notation. So the lower right index of the Christoffel symbol and write alpha, and the left index is beta, and then I will have this. If it is with respect to a vector, say A, this is my notation. This means, but now there is a plus sign. Similar thing I can write for tensors of type 2, 0. So this is a derivative of this with respect to, say, gamma. So this will be, but now I will need to write two Christoffel symbols because both the indices are upstairs here. Both the Christoffel symbols will come with positive sign. I'll have one of them here, and let me write the other one where I will have the other. The gamma will come in the second index. So this must be an index which is running. So let us use mu for that. So if you want to have the similar indices in the left hand side and the right hand side, this is what I should have now. Okay. Similarly, I can have one for 0, 2 type tensor, which is now I will not have Christoffel symbols with plus sign but rather minus sign because the indices are downstairs. And what should I have here? So I know that this will be gamma, alpha, mu, and then my t. Now if I look at the tensor, it was alpha, beta. Alpha has to be replaced with mu and beta will remain as it is. And in the next one, I will replace beta and alpha will remain as it is. And I can have a mixed case also where one index is up, one index is down. I leave it for you to figure out how to write this down. For the index which is upstairs, I'll have a plus sign for the Christoffel symbol. The index which is downstairs, I'll have a minus sign for the Christoffel symbol. Now, this is also sometimes you will see the notation as when I write in vector form. That is another notation for the covariant derivative. So these are covariant derivatives up to tensors of rank 2, where the total number of components I need to put in the mapping that is called tensor is 2. So 1 and 2 that we have written down. Also, one thing one should remember is that these equations are tensor equations. So if I say that in some case T alpha beta semicolon gamma is 0, it should be same, that equation should be valid for all reference system. So tensor equations, and this is something that we will use, tensor equations are valid. This is why we are trying to use the notion of tensor in general relativity. The components of the tensors will change, but the equation will look same. So this is also called general covariance. Okay. Now, having said that, let us ask the question now, what is the covariant derivative of the metric? Metric is a second rank tensor of the form, so you are talking about this form. And let us ask the question that what is the covariant derivative of the metric? This is our question. Okay. This is obviously is of importance for us because metric is something that you said has all the information that we need in general relativity, most of the information. So we'll have a look at this. Now, the first thing that you realize is that this is a tensor equation, and this tensor has three indices, all downstairs. So this is a tensor of form 0, 3. So if I can figure out the right hand side in how the equation looks in one coordinate system, I am good enough to then I can figure it out in all coordinate system. Now we are talking about here for this lecture, we are talking about curvilinear coordinates. Now what are curvilinear coordinates? For example, I have the normal Euclidean space, which we'll define later more explicitly, but like in the general space that we always work with in classical mechanics, we can have a Cartesian coordinate system, we can have a polar coordinate system, we can have a cylindrical polar coordinate system, etc. Cartesian system is one where the basis vectors doesn't change if you go to different places in the coordinate system. But when you are dealing with curvilinear with like spherical polar coordinate system, the basis vector does change. So those are the curvilinear coordinate system. Spherical polar coordinate system is a curvilinear coordinate system. But you see, the basic motion or the basic geometry that we will try to describe should not have any attachment with the particular coordinate system I choose to describe that basic geometry or motion. Which means if I can figure out what a tensor equation is in one of these coordinate system, it should be same, the form invariant, it should have the same form in all the other reference system. For example, let us figure out what is G alpha beta gamma in Cartesian coordinate system. Okay, so let us figure out what is this in the Cartesian coordinate system. Well, by definition, this derivative is, let me write down explicitly for the time being, minus, because all the indices of G are downstairs. It doesn't matter if I write beta mu or mu beta because we know that G is symmetric. So this is what the covariant derivative is. This is this quantity in any coordinate system. So in the Cartesian system, let us see what these are. In the Cartesian system, G alpha beta is just the diagonal 1, 1, 1. So G alpha beta are constant in Cartesian coordinate system, which means that with change of coordinate, they will not change, so this will be 0. And remember that these quantities, which are the Christoffel symbol, came from the fact that you are taking the derivative of the unit vectors. But the unit vectors also doesn't change at different positions in the Cartesian system. So if the derivative of the unit vectors is 0, their components are also 0, so these are also 0. So when I say these, I mean the Christoffel symbols are 0. So it's 0 plus 0 plus 0. So in Cartesian system, this is equals to 0. Now that becomes an equation, right? So that becomes this equation where I write G alpha beta semicolon gamma, which is the covariant derivative of G alpha beta, equals 0. So this is an equation. It has an equals to sign. And what does it mean? Remember, this means all d to the 3 components in d dimensions are 0. It's not one component which is 0, it's all components of this tensor are 0. Well, you see, if all the components of a tensor is 0 in one reference frame, whatever coordinate transformation you do, the coordinate transformations, the components of this in other reference frames are linear combinations of the components in this reference frame, and in this reference frame all components are 0. So this should be true everywhere, true in all reference frames. Here we are not quite talking about a general coordinate transformation, because remember, when I say all reference frames, I essentially mean that I should be able to have a transformation rule well defined to go from the Cartesian frame to that particular reference frame. Okay, then only this is true. Okay, so we have learned about one property of the metric, that the covariant derivative of metric is 0, and which is again true in all reference frames. Okay, so next we'll study the properties of the Christoffel symbol. Now, the Christoffel symbol, let me write it here, it's a mu alpha beta. So downstairs there are two components, and we have not talked about, we said that it has d to the 3 components, but we never said that these components are the components of a tensor. Okay, so let me remind you of these facts. Okay, all right. Downstairs it has two components. The first question we ask is that, is the Christoffel symbol symmetric about its downstairs components? Now, to do this, we again look at the following covariant derivative. So, what's the covariant derivative? The covariant derivative is, let's first look at a normal derivative of a scalar field, but I'm taking two derivatives. So, this is essentially del 2 phi. If I write in longhand, removing the shorthand notation, sometimes it is useful. Which you see, the way I do the differentiation doesn't matter. So I can do the differentiation with respect to the gamma index first, and then with the respect to the beta index, and vice versa, which means that this is equals phi gamma beta. So this is not covariant derivative, right? This is normal derivative. say that the actual thing that I wanted to look at is the following, is phi comma beta then semicolon gamma. So remember that phi beta is a one form. So this is a covariant derivative of a one form. And I wanted to compare this with phi gamma semicolon beta. Okay. This is also covariant derivative of a one form. But in Cartesian, again the Christoffel symbol vanishes. The unit vectors doesn't change with different positions, which means that this is same as this in Cartesian and this is same as this in Cartesian. So in Cartesian then if I compare this and this, I say that I get this equation. So these two are same. So that's now is the equation of a tensor of type 02. The left hand side I have a tensor of type 02, right hand side I have a tensor of type 02, and this is a tensor equation. If that is true in the Cartesian, this should also be true in any arbitrary system. So this is arbitrary system. Now let us break this down in terms of the normal derivatives and the Christoffel symbols. So this will become, this is again in arbitrary system. So I need to bring in the gamma, which will come with a minus sign because all the indices are downstairs again. And what will this be? This beta gamma mu phi mu. How do I write this down? So this is a one form with an index beta. So that is this thing. So we can write this as like p beta. And this is again one form with index mu. So this is like p mu. And now probably it is very clear to you. How do I write this down? If you look at the right hand side, which is equals to the left hand side because it's a tensor equation, is phi gamma beta minus this should be gamma beta. Remember that whatever it is differentiated by comes at the end of the Christoffel symbol. So that is beta in this case. And then I will have again phi mu. If I compare the left hand side and the right hand side, the first thing I realize is that, let me highlight with colors, this is same as this. It doesn't matter which way I do the partial differentiations. And then this is same as this. The only way for an arbitrary phi this equation is true is that the Christoffel symbols has to be symmetric in its lower indices. So these are symmetric in its lower indices. That is why it is true. All right. Now, it's all right. We have got something called the Christoffel symbol, but do we have a way of calculating it? Can we calculate the Christoffel symbol? Now, the trick comes from the fact that the covariant derivative of the metric is 0. So, I write, say for example, I start by, so this is calculation of, so how do I calculate this? It will turn out that this is related to the metric and we can calculate it once we know the metric. Okay. So use the fact that the covariant derivative of metric is 0. So what do I write? I write, say, nu alpha semicolon beta. So let us, so this is equals to 0, which implies that g nu alpha comma beta, not semicolon, sorry, comma beta minus two gammas that will come because it's a covariant derivative of two forms rather. Both the indices are downstairs. So, and then it will be equals to 0. So I write those gammas in the right hand side. Okay. The way I am writing is, so let me write the second one and then it will be clear to you. So then I write, why I am doing this will be clear again. So let me first do it and then we will discuss about it. Okay. So let's write beta nu alpha. This will give us so remember the derivative with respect to the derivative with, so that index will be the right hand side index. Here I will have a dummy index, and in the first place of the downstairs of gamma, I will have one of the index of the g. The other index will stay with the g. And here again, so mu is the dummy index, so g will get that dummy index. The second index downstairs of gamma will always be the derivative, so it's alpha. And the first index previously replaced beta, so now we'll replace nu. So in place of nu, I will write mu, and this will remain as beta. And then finally, I will take one more, which is alpha beta semicolon nu equals 0. I'm sorry. Okay, so I have just written down three covariant derivatives, just interchanging the indices of g. And what I will do now is that I will add these two and subtract this one. And let us write down. Let us write down the left hand side. The left hand side is G nu alpha beta plus G beta nu alpha. And now I come gets the minus sign alpha beta nu. Let's examine what do I get in the right hand side. So I have nu beta downstairs here. I have beta nu, but remember Christoffel symbols are symmetric, so this is same as nu beta. And I have alpha nu here, alpha mu here, and mu alpha here. Again, they are symmetric. G is also symmetric. So this term is same as this term. Because I have chosen positive for the first and the negative for the third, these two will cancel out. Okay, so let us look at this term now. This term is nu alpha mu and beta mu. So it's same as this term. The first one comes with a positive side, the second row, and this comes with a negative side. They will also cancel. Now the rest of the terms are again same. So this term and this term is again same, but both of them comes with a positive side sign. So this is just 2g nu mu gamma mu alpha beta. Now I want to write everything in terms of gamma. You can see now I can write gamma in terms of the derivatives of g, but not quite so because this thing is multiplying it. But I can use a nice trick, which is that here this nu is one index, so I multiply this entire thing with a delta nu say eta. Obviously, I have to do the same thing in the left hand side as well. So this, remember, is not simple multiplication. I am also summing over nu. So what I do is I multiply this with a g, but this g is inverse g of the metric, where this g is like nu eta, and this is not a simple multiplication, it's also summing over the index nu, as you can see. And then obviously I have to multiply both sides. If I do that, what happens to the left hand side? See, I now get two g's, and these two g's will multiply to give me a delta function. I'm sorry, a Kronecker delta, which is this. So now, once I sum over mu, the only place where it is non-zero is mu equals to eta. So I get finally eta alpha beta equals 2 goes the other side, half g nu eta g alpha nu beta plus g beta nu alpha minus g alpha beta nu. So that is the expression for Christoffel symbol in terms of metric and its derivative. So this expression essentially let me calculate this Christoffel symbol once I know the metric. It's very useful. One thing you should check is now in this form, can we prove the symmetry of the metric just from this form? Okay. Now remember that, let me remind you of this form, that this quantity 0 is 0 in Cartesian. When I say that, it essentially means that all d to the 3 components, are 0 in Cartesian. And it is non-zero, can be non-zero in a curvilinear system. Right? So which means that this is not a tensor of form like 1, 2. One may be tempted to write this down as a tensor of form 1, 2, but it is not a tensor of form 1, 2. Because if it is a tensor of form 1, 2, then there is no way you can get non-zero components in one coordinate system when all the components are 0 in the other coordinate system. Okay. Part of this can be considered as tensor, but that really is not of much importance for us. So we'll just state that if I consider all d to the 3 components in d dimension, they are not components of a tensor. They does not transfer the way such a tensor should transform. Components of such a transfer should transform. This you can verify starting from here. So you know how the metric transforms. So you should be able to figure out how the Christoffel symbol transforms. So that I leave for you as a homework. Alright, so that is all that we'll discuss at this moment about the Christoffel symbols and the curvilinear coordinates. Let us now come to a real example and a simple example. So in this case, I choose d equals to 2 and I choose the spatial part, and it's called Euclidean Space. What it means exactly will be clear in the next lecture probably. So that is my setup. In this setup now, this is the space, underlying space, which doesn't care about which coordinate system you are in. Here, we will choose two types of coordinate system. One is the Cartesian, which is simply x and y. Other is the 2D polar, which you can denote as r and phi. Okay. So one is Cartesian, the other is a curvilinear system, because as you know that 2D polar is a curvilinear system. Okay. So what are the basis vectors? The basis vectors in Cartesian, so if I call them E1, E1 is essentially my x cap and E2 is y cap. In polar, E1 is, should I write E1 prime because we'll do a transformation shortly. So this is r cap and E2 prime is phi cap. It's a connection between the coordinates or the mapping of the coordinates. What are the mapping? Well, r square, if I want to get, I have to do x square plus y square. And if I want to get phi, I have to do tan inverse y by x. Here, if I want to get x out of these coordinates, I do r cos phi. And if I want to get y, I do r sin phi. So once we have these, we can figure out the transformation rules. So let's do first for the basis vectors. And we will go from the non-curvilinear to curvilinear, that is from the Cartesian to polar. So if I write my notation for the transformation rule, that if you remember is given by this. Let's work it out. So U1 prime is r cap. So r cap is, there is a sum over alpha and I have only two coordinates. So the sum is alpha equals 1, alpha equals 2. So del x1, the first coordinate in the Cartesian is x itself. So this is del x and then del r, because x1 prime is r. And what this will be? X cap, because I have x over there. And then the next one will be del y, del r, y cap. So that tells me that r cap is, what is del x del r? Well, I can use this. I do del x del r, I get cos phi. So this is cos phi x cap plus sin phi y cap. I urge you to calculate the phi cap by yourself. This you will see will come out to be r into minus sin phi x cap plus cos phi y cap. This you can just exactly calculate the same way. One I have done, the other you should do. So I got the r cap and phi cap in terms of x and y cap. Now why it is important? Because I know that x cap dot x cap is 1, so is y cap dot y cap. These are true for all positions x and y, that's why it's not a curvilinear system. And this is equal 0. And I can use these to figure out all the other things. But remember also that what I have written down here is essentially the fact that gxx, which is this, equals 1 equals gyy, which is this, and this is nothing but gxy or gyx. They are same. But let's look at the one forms. How does the one forms transfer? So let us write down what this will be. This is supposed to be, by the way, this is equals d r prime. I will not write prime for the r, so this is dr. And this is nothing but del x 1 prime del x alpha, and then this. So which, if you calculate now, dr will be, now what is x1? X1 is r. So this is del r, del x, and dx plus del r, del y, dy. How do I calculate del r, del x? Well, now I have to use these relations. So r square is x square plus y square. So let us work it out here. Again, I will do one, you will do the rest. So r square equals x square plus y square. So r del x is essentially x. So del r del x is x by r. But x by r is nothing but cos phi, which you can see from here. So this dr is cos phi dx plus sin phi. If you calculate d phi, you will see this is a little bit non-trivial. This is sin phi by r dx, sin phi with a minus. Okay, so these are again the relations, the one forms in the two system. We can now calculate the metric in the curvilinear system. How do I do that? Well, r cap dot r cap is grr. What will that be? Let's have a look. So r cap I have here. If I do a dot product with this, x will do dot product with only x to have a non-zero number. So it will give me cos square phi, and y dot y, the dot product with y will have a component of sin square phi. They'll add up to 1 essentially. So this will be 1 simply. R cap dot phi cap. Let's see what I will get. So if I do r cap dot phi cap, so again x dot x will have a component of cos phi minus sin phi. So minus of cos phi into sin phi. And y dot y cap will have a component of plus of cos phi into sin phi. So they will essentially cancel out. So that term is 0. So this is g r phi or g phi r. They are 0. So I am left with phi cap, phi cap. Phi cap, phi cap. What will that be? So phi with phi. So again, minus sin phi square and cos phi square will give me 1. But you see there is a r sitting outside which will come twice. So this will become r square. So grr is r square. So g is still diagonal. But it is not constant. It is 1 and r square in the diagonal. And you can figure out what g alpha beta upstairs will be. They'll be also diagonal, but now 1 and 1 by r square. That is trivial to see, so I will not show you explicitly. Alright. Now that we know the metric, can we calculate the Christoffel symbols? Okay, so let us see let's first write down the definition. So alpha beta here, nu here is half g say mu nu and I'll need to move it towards the left a little bit because it will soon go out of. Okay, so let us first write down what is the definition of this in terms of the metric. This is half G mu nu, and I have G alpha mu beta plus G beta mu alpha minus G alpha beta mu. Right? So that is the definition of Christoffel. And let us write down here that the metric components GRR is 1 and G phi phi is R square. GRR upstairs is also 1, but G phi phi upstairs is 1 by R square. So these are the metric components which I will need to calculate the Christoffel symbol. Now let us ask the question, what are the different types of Christoffel symbol that there is? So I can have the upstairs can be R. For that I can have this as RR, this as phi phi, and this as R phi. The upstairs can be phi, then this can be phi phi, and phi, this can be R phi, phi, this can be RR. Okay, these are the 6 cases that I can have. Now let us first look at the cases where the upstairs is R. So nu equals R. The new index is R. So this is R, and this can be anything. So let me write still alpha beta. So alpha beta can be other R, phi, etc. combinations. Let's see what is there in the right hand side. Well, then right hand side I have this G, which is mu nu, but the nu is R and G is diagonal, so mu also has to be R. Otherwise the right hand side will vanish. So you immediately see that you get alpha R comma beta plus G beta R comma alpha minus G alpha beta comma R. Okay. Stare at it a little bit and see that out of these 3 possibilities, which one we need to calculate and others we can just write down as 0. You see, the first 2 indices here has with it R. And remember, all the components of G are either constant or function of R. None of them are function of phi. Okay. Is either 1 or R square or 1 by R square. There is no function of phi. There is no phi dependence in any components of G. Okay. And all the components which has RR, so GRR downstairs and GRR upstairs are constant, are 1. So if I look at these two, one of them are already R, the other has to be R, otherwise they will not be diagonal. But even if they are R, so I have a derivative with respect to something else, but GRRs are constant, so these are always 0. So these are always 0. So I'm left with this term. But you see, this term is a derivative with respect to r, and the only g alpha beta component which can have a derivative with respect to r and still be non-zero is g phi phi. So alpha beta can only be phi phi. So the only non-zero component is r phi phi here. And what is that component? Half grr is 1 and g alpha beta, which is g phi phi, this is times g phi phi is r square, so that is 2r. If I do the derivative, the entire thing is just r. And the other things, which is Christoffel r equals Christoffel r phi, they're all 0. Let's look at the phi ones. So when nu equals phi. Okay. So I'll do the same trick and write it down. Once you do it for several times, you will be quite fast in doing these things, looking at the symmetries and all the kind of informations that you're using will be quite fast. So anyway, so this is phi alpha beta equals half. The same token, this has to be phi phi now, and g alpha phi comma beta plus g beta phi comma alpha minus g alpha beta comma phi. Why do we see? There is nothing which can be a derivative, no g component which is a derivative of phi. This goes out. Yeah, I forgot the minus sign here. And you realize that this r or beta, this alpha or beta has to be phi. One has to be phi and the other has to be r. Because you see, if alpha is r, then g alpha is 0. But then beta has to be phi, because if alpha is r here and beta is phi, then that phi phi comma r makes sense. So again, the only thing that will survive is one r, the other phi. Which one doesn't matter because it's symmetric. So this is equals half of, now g phi phi is 1 by r square, and this is delta of r square by del r, which is 2r. So this becomes 1 by r. The other two, which is all phi and rr, are 0. So only two components of the Christoffel symbol survived. Okay, so we are almost at the end of the discussion. Just let me show you one thing that we discussed in the last lecture, and we use the Christoffel symbol and we'll see something familiar that comes out. Okay, so say I have a vector A. So I have a vector A. So this vector, so in the Cartesian, so let's write the Cartesian is C, has components Ax. So this is Ax x cap plus Ay y cap. In the Cartesian, if I want to write the divergence of A, that is del Ax del x plus del ay del y. The same vector in polar, cylindrical polar, which we are discussing here, has these components ar and fi. If I want to write the divergence of this, then I have to use the covariant divergence, which is defined as what is this? This, if you remember, is a alpha alpha plus a gamma. This is gamma alpha. So this is alpha, this is alpha, this is mu, a mu. This is it. So the left hand side is the divergence of the vector A still. Doesn't matter which coordinate system you write, this is coordinate independent rotation in the left hand side. Let's see what is there in the right hand side. So first I have this sum over alpha, so I have del r here, and then I have del fi, del phi, sorry. Now, let me just to remind ourselves, let me write the two non-zero components of the Christoffel symbols. R phi phi is minus r. So this is r phi phi is minus r, and phi r phi is 1 by r. Okay. So let's see what do I get in the right hand side of this expression, which comes with the Christoffel symbol. So here with this I will have, so if I choose mu to be r, then I can only have this component, which is phi r phi ar. Can I choose mu to be phi? See, if I choose mu to be phi, then so let us write which by choosing mu to be phi. So this mu I am talking about. So this is a phi. So this will be phi, and I should have the same index here and here, but I can have r and r, that is 0. I can have phi and phi, that is also 0. So this term not need to write because this is all 0. So let us remove this term. This is all that I have of the divergence. And what is this? So del ar plus phi r phi is 1 by r, ar plus del a phi del phi. I can write this in a more interesting form. What will this be in terms of the what will this be when we write it in the more familiar way? So this is del r of so it works out. So when I do del r of r ar, first I take the derivative with respect to r, I get ar by r, which is this term. Then I keep r as it is, which cancels 1 by r, so I get del r of r. But if you have studied already, if you've written down divergence in 2D polar, that is how it looks like. And you can derive all these formulas now that you know. how to go from the Cartesian to the curvilinear system. Okay, I'll give you some exercise where you will be able to figure out many such transformations, like we could have literally looked at the Laplacian or the gradient, etc., etc. Gradient is essentially the covariant derivative, but to connect them from the curvilinear known forms that we know. So those I will keep in as in exercise. So this completes our discussion on the curvilinear coordinates. Next, we will go to one stage up, where still in this case we said that we are dealing with this thing called the Euclidean space. What do I mean by that? What are the other types of spaces that there can be? One, we are already familiar with Minkowski space in case of special relativity, etc. So those are the things that we'll take up in the next discussion. That's it for today.